Hi everyone, in this short video, let's have a look at the results of mitochondria segmentation in electron microscopy images using both machine learning and deep learning techniques. And the goal here is to understand how machine learning quickly reaches its limit when it comes to segmenting these complex objects against complex background. A quick note on the training, both machine learning and deep learning models were trained on exactly the same data using same annotations, and we have used 16 annotated images. And the machine learning, of course, uses features and a classifier. In this case, the features were extracted using a VGG16 pre-trained network, and we used 256 features. And those features served as an input to a random forest classifier. Together, we have a conventional machine learning algorithm. And for deep learning, we used a unit framework where the encoder was replaced by EfficientNet encoder. Let's have a look at the results now. And here is one of the images that we actually used as a training image. And here is the result from machine learning. So as you can see, machine learning does an amazing job at segmenting this image, almost identical to the deep learning here. So both machine learning, deep learning, other than these two little dots that the machine learning thought that were mitochondria, we got identical results right there. Please note that this image has been used for training. Now let's have a look at the images that were not used for training. So on the screen, you see three images. The central one was exactly the same one we saw in the previous screen. The central one has been used for training, and the one on the left-hand side directly came from the slice below the central one, and the one on the right-hand side is from the above in this Z direction. So these images all look identical, but when you look at the results, machine learning did a very good job at segmenting the central image because that image was used for training, whereas it failed at properly segmenting images in slice 49 and slice 51. This shows that machine learning is overfitting on the data that it has seen before. It remembers that data, but then it doesn't remember anything about slice number 49 or slice number 51. Both images look identical to slice number 50, but the results are different. What does this mean? This means that you cannot just train your model, your conventional machine learning model, on a training data set and expect that to work on the entire volume of your data set. Forget using that on other data sets, but within the same data set, you may not be able to apply that machine learning model to other slices in that data set. Whereas deep learning, as you can see on the screen, does an equally good job on the training images and also on the images that were not used for training. So this clearly proves that deep learning is the right technique for EM images, for volumetric EM images, or if you want to train models and use those models over and over for a long period of time. So the take-home message in this case, as you can see, is deep learning provides consistent results throughout the data set. So please consider deep learning when you're trying to work with EM images, especially the ones that offer the type of complexity that you see on the screen right now. Thank you.